All right, hi. Yeah, it's great to be back at the Simons, and again, thanks to the organizers for organizing another wonderful workshop. So many of the problems we face in statistical estimation are essentially optimization problems. And they're noisy optimization problems because we're typically trying to estimate the minima of some function where we only have noisy access to the function. Trickle in. So consider the problem of linear regression. Right? We want to find the best fit line with regards to some unknown underlying distribution, and we only get samples of the function. We get n samples, and we'd like to find the best fit line. Well, we'd actually like to find the best fit line with regards to the distribution. What we often do in practice, we take the best fit line on the data. Okay? And in high dimensions, this is a question of estimating a linear relationship with n points in d dimensions. And this is quite expensive if we're going to try to find the best fit line on a given data set in high dimensions. We never do this. Right? This is one, it's definitely poly time. When n and d are large, we just can't solve the linear system exactly. Okay?
How large is large in practice?
So the things I've been working on are dimensions in the order of tens to hundreds of thousands, and n is also very big. These are problems where we can't fit our data into memory, which is a headache. And in small problems, we know how to do this. We just do backslash in MATLAB. On large problems, it's a headache, and we'd like this really is the question. We'd like to automate it in an automated way. We'd like to do well on these problems. And what makes these problems interesting is we don't need exact solutions, right? Because the data is noisy. And that really is the right question here. And that question really highlights a lot of the trade-offs we face in computation and statistics, because at one end of the spectrum, what do? We'll just do something quick and dirty like stochastic gradient descent. It's fast, it's easy to implement, it's super light on memory, we just pass through our data. It doesn't give us all that good answers, but maybe it doesn't matter that much because our data is noisy. Okay, the other end of the spectrum, we could burn a lot of computation time, get a very accurate answer. Is it worth wasting the extra computation time? And this is really the question. So what would you do here? Okay, and in practice on these very large data sets, by and large, people use SGD. This really is the winner. Okay, and I just want to point out this is a very relevant question right now because there are a lot of efforts underway to try to automate machine learning and statistics algorithms for pretty large data sets. So I've just listed a few here. These are sometimes open source packages, sometimes they're private. Some of these are run by companies, some are at universities. Berkeley's is ML based, it's open source. A very popular one is VW from John Langford, and one of the reasons this is so popular is it really has a very good implementation of various convex optimization solvers. Like people have these big data sets, they'd like to get something that works out of the box, and this is a pretty nicely optimized one.
Question?
Yes.
Packages that do stochastic gradient descent,
yes.
Do they pay attention to the numerical issues?
In a sense, they don't, in that they're definitely not competitive with backslash, and the intuition for that is they're typically used in learning problems where data is noisy. They're like if you actually look at the numerical answers, they're terrible, but the idea is that since our data is noisy, maybe it's good enough for prediction problems. And it's very clear people want better things, because if we actually look at smaller data sets and solve things very, very well, we'll often get better performance. So by and large, these are used because it's all we can really do on these big data sets. But the question is sort of related to your question as well, that back in the 70s, we got these very nice numerical linear algebra packages, and we don't have to think about matrix inversion or solving linear systems. And we just hit backslash, it solves the problem well. And a very nice question would be, can we do something analogous for our statistical estimation problems where we do things very, very well, put them into packages so people don't have to think about them. Okay? But to do this very well, we really have to get the details right. Sort of related to your question, which is, and it's very clear the detail here isn't numerical precision because we don't care about, getting the 10th digit of accuracy if our optimization problem is noisy. Okay? So the question is, how do we phrase this carefully, and how do we solve this? And we'd like to do well on every problem. And really the goal here would be, for our basic core machine learning problems, can we automate them and have people forget about the details? Okay, so what's our goal? Well, we'd like to do well statistically, and we'd like to do it quickly. So again, the problem is we have some optimization problem L of W. We think of L of W as some expected loss with respect to some underlying distribution. Think of something like linear regression. So loss is the square loss, W is a line, a point is just some XY pair. Okay? And we only have access to this function with n samples. Okay? But you want to do well against L of W. We don't care about doing well on the data we see. And we're going to measure ourselves by how well we do compared to the best. So you get n samples, you come up with some estimator W hat n, and we measure ourselves with what I call the error. It's sometimes the excess risk or regret. I'll just call it the error. And this expectation is with respect to the randomness in the training sample. So is the setting clear? Okay. So this is what I'd like to do. But we'd like to do well on every problem. So this is, so let's try to make a more stringent criterion and see what we can do.
You're assuming the distribution T is known?
The distribution...
Script T.
No, if it was, no, but we have access to it from samples.
Okay.
That's right. So this is...
Do well uniformly somehow over some class of T's, or?
So that's right. So ideally, we'd like to do well with some restrictions on the loss function, but ideally, we'd like to do well on every distribution. But in a sense, look, when you hit backslash, it'll do well on every instance as a function of condition numbers and things like that. Right? And we'd like something analogous here.
I don't know what backslash is.
Oh, so it's basically the one take-home message from numerical linear algebra is don't write matrix inverse when you're solving a system, write backslash because it does all the details correctly. But the point is we want to get all the details correct. It's going to depend on various properties like condition numbers and so on, but we'd like to do that correctly in the statistical regime. But in particular, suppose we didn't have computational constraints, right? We would just like to use the best fit line. So this is sometimes referred to as the empirical risk minimizer or the M estimator. Right? If we didn't have computational constraints, just compute this and we'd use this. Okay? But this is costly because, memory-wise, it could be a headache. It might be poly time. So what we're going to ask to do is look at the rate of convergence had we used the best fit line, and look at the rate of convergence of our estimator. Okay, so this is how well we're doing in comparison to how well we would have done had we computed the best fit line. So the question is, can we drive this ratio to 1 on every problem? Okay? So it's not just saying asymptotically I'm going to get the right answer. I want to get the right answer at the same rate as if I computed the best fit line. Now obviously you could make this ratio 1 if you just computed the best fit line. But that's costly. So we'd like to get this ratio to be near 1 on every problem where we're mindful of our computational constraints. Okay, is the problem clear?
In the case of regression, what does the expression mean?
So the numerator is literally how far off the least squares estimator is from the right answer, because the best residual error, and we compare our best residual error to that. It's exactly that. You sure?
So you're not regularizing. Is this?
You can put in autoregularizers. Let's get back to that. You can put in autoregularizers. Okay, but let's just do it for regression as the.
It's not an issue.
Okay, good. So this is really the setting. Yep.
Why are you competing against this particular?
So if we could do better than this, we would solve a big question. Basically, there's 100 years of statistics essentially arguing you really can't do much better. You can shrink a little, but put it this way: if I want to measure a mean, the best you can do is use the sample average. You can shrink a little, but we aren't going to try to get a better statistical estimator. Assume Statistics has told us this is a good estimator, and the reason I'm doing that is because there is a body of work essentially arguing the M estimator, ERM, is a good estimator. Okay, and now we want to do well according to this estimator. And this is what people do when they run these optimization packages. They're trying to compute this estimator. So it's a way to try to phrase this issue of how accurate is accurate enough. And we want to do well on every problem. So this is the criterion. It's stringent. And notice that, if we think about solving a linear system, this is an interesting question because, solving a linear system is a big open problem in computer science theory. But we're not trying to get bit precision here. We're giving a different criterion for solving the linear system. Okay? So that's where we're thinking about this trade-off. Like if we just want to drive this ratio to 1, how can we do it? So we good?
Can you comment on doing multiplicative versus additive? Is this?
Forget about. Let's do. This is multiplicative, but it's on the regret. So that's the important thing. Okay. So it's. Okay. So the main results are going to be that you can actually drive this ratio to 1. You can do this with a one-pass algorithm. The memory is basically the same as order of 1 sample. The algorithm is trivially parallelizable. You really can drive this ratio to 1 on every problem under mild restriction. See, these are problems like linear and logistic regression, various generalized linear models. And this algorithm is going to have a super polynomial dependence on the initial error. And by that I mean all algorithms we use in practice start at a point, and you want to have a very weak dependence on your starting point. So this algorithm is going to crush that dependence on the starting point. Okay? So in a sense, like yes, I said there's trade-offs between statistics and computation, but that's a bit misleading. You really just win here. You can get this in one pass. And there's definitely related work that's somehow been forgotten. There's a very nice asymptotic result by Juditsky and Polyak. But it's a very relevant question. Like literally like the last 5 to 10 years, people have been asking this question over and over again. Okay. So I'll try to give you a flavor. So the algorithm's got to be simple, right? Because you're not holding much in memory. It's really the same complexity of SGD, and you're nailing the problem. Okay. So let's see how we do this. So the basic outline of the talk is, let's just forget about computation for a moment and look at statistics. Let's forget about statistics for a moment and just think about optimizing on the data we have. Okay? And then we'll put the two together. So let's just ignore anything computational right now, and let's see what's the rate of this empirical risk minimizer. Okay? So if we compute it exactly, what's the rate of convergence of that estimator? Okay. And again, think square loss as the example we're going to be considering. So these are statistics land. They're going to be kind of the assumptions for local asymptotic normality. So basically, suppose you're measuring a mean. What's the rate of convergence? It's the variance over n. Okay? And that's basically what it is here. So I'm going to define this quantity sigma squared, which is we're going to look at the norm of the gradient at the optimal point, measure how large it is under the Hessian at the optimal point, the inverse Hessian, define that to be sigma squared. And the rate of convergence of the empirical risk minimizer is exactly sigma squared over n. This is basically like Cramero. Like intuitively, it's like, if you start at W star and get a random sample of data, so W star is the best point, you're going to move. And if you did a step of Newton, this is how far you'd be off. And this is essentially the rate of the ERM. And the point of this, so there's no computation here, but this is what we'd like to get, and we'd like to get exactly sigma squared, not just 1 over n. This is the exact problem-dependent constant we want. Okay, so is that clear? That's really just, if we're doing things right, our rate is going to be sigma squared over n, and we want to quantify the rate at which that occurs. We want that to occur quickly.
If you want to divide any constants also?
We'd like the constant, fine, 2 sigma squared over n is also fine, but we don't want dimension or condition number. Yeah, so the main point is you don't want dimension or condition number times sigma squared over n, and that's what SGD will get you, which is why it's really quite bad. Okay, we good with?
Strong convexity assumption?
Yeah, because the Hessian exists, but only locally around the, yeah. So basically these are assumptions for like local asymptotic normality. Think regression, which is basically local asymptotic normality, generalizes. But think linear regression. So that's statistics. We're done. Let's ignore it for now. That's the rate we want. Okay, so now let's switch to computation. And for computation, ignore the statistics problem. Suppose we just want to optimize a sum of convex functions. So before L was an expectation, ignore it for now. Let's just think about optimizing sums of convex functions. And there's been a lot of very, very nice work in the last 5 to 10 years on optimizing sums of convex functions. And the reason this work is essentially come about is because this type of optimization problem comes up all the time in machine learning problems. And a lot of the work is how do we get linear convergence for optimizing sums of convex functions, like optimize it quickly. But there's a question of why do we care about linear convergence if the reason we're solving these problems is because they're coming from statistics problems. But the main point here is, this is a very common optimization problem that's being studied recently. And there's a lot of beautiful work on kind of numerically precise algorithms for this particular paradigm. And I'm going to cover one really elegant algorithm by Ri Johnson and Tong Zhang, which we're going to utilize. But for now, forget about the statistics problem. Let's just look at this particular paradigm. Let's look at stochastic gradient descent to see how it goes wrong and see how we fix it. Because SGD is what everyone uses. Okay? So let's just start with SGD. And let's look at SGD for this particular optimization problem. Okay, we good with that? Well, we want to just optimize. Forget about generalization. We just want to optimize the sum of convex functions. Okay. So let's look at SGD. It's an old algorithm. It's super simple to implement. What do? Well, at each time step, so we're going to think about fitting this line on this sample of points. So there's no distribution. So what do we do with stochastic gradient descent? We're just going to sample a point randomly and try to adjust this line so as to better fit this point. Right? So we sample this point. We're going to adjust this line by moving the gradient so it better fits that line. Right? We do that, moves. Eventually we do this and we get to the right answer. Okay, so why is this a terrible algorithm from a numerical perspective? Well, suppose you start at the right answer. Right? Now you sample this point. SGD is still going to move you. This is terrible from a numerical perspective. This is why the precision is actually very bad, because you're bouncing around all over the place. Right? And this is why batch gradient descent, if you're at the right answer, you don't move, because the gradient's 0. Right? Like if you actually computed the gradient of the entire function, you sum over everything, that gradient's 0, you don't move. But with stochastic, and that's why with batch gradient descent, you get geometric convergence, or linear convergence. With stochastic gradient descent, like the only way you can get this thing to converge is by turning down the learning rate. And that means your algorithms are sensitive to learning rates because, and this is really a frustration in practice, because if you get things wrong with setting your learning rates, you really do pay for your mistakes. Okay? So how do we fix that? Okay, so this is, and again, we're ignoring statistics issue right now. We just want to think about a better way to implement SGD. And think about why it's going wrong. As you're cycling over the data set and you're turning the learning rate down, the algorithm is converging. Right? And eventually you should realize you're doing something stupid. Right? Like every time you're touching this point, you're getting kicked in exactly the same direction when you're getting to the right answer. And eventually you should start realizing, look, there's systematic bias in my algorithm. I shouldn't be moving in the same direction every time I touch this point. Right? And that's really this beautiful idea of SVRG. It basically figures out the systematic bias in this algorithm, takes it out, and gets numerical precision. It gets linear convergence. Okay? It's a very intuitive idea. Like if your algorithm is working at all, you should start realizing every time you hit the same point, you're going to get kicked in the same direction. And you want to remove that bias. Okay. So this is SVRG. Okay, so we're going to compute the gradient stages. Let's just start this algorithm as if we're at the right answer. So the first thing this algorithm, the stochastic variance reduced gradient descent, is going to do, it's going to compute the gradient at some point. Okay, suppose we start at the optimal. What's the gradient at the optimal point? 0. So let's ignore the first term right now. Okay, so, and this thing is 0. So what this algorithm is doing is it's subtracting out the gradient of the point you're at with respect to the gradient of some reference point. And if this reference point is optimal, and you start at the optimal point, you don't move. Okay? Right, that should be clear, right? Because if W total S is the optimal point, and I start at the optimal point, this algorithm doesn't move, because I'm just basically subtracting out the gradient at the optimal point. Exactly. We don't know the gradient at the optimal point. We do know L because we have the sum of convex functions.
I thought L was the expectation.
That's what I'm saying. Forget about statistics for now, because there's no way we're going to get numerical precision on statistics problems. So for right now, forget about the statistics problem, and we're just trying to minimize the sum of convex functions.
You renamed L to be.
Yes, I renamed L to be this, right? So, but the point is, if we're not at the optimal point, this isn't going to work, because we're biasing our gradient. Okay, so what do we need to get SGD to work? We need to follow unbiased estimates of the gradient. That's basically why SGD works. Okay, so the idea of this algorithm now is we're basically going to, this blue term is our best guess of the systematic bias, and we're going to subtract it out. Okay, so we have some W twiddle S. We're going to update that every once in a while. The first thing we do is we compute a batch gradient. Okay, and then at every sample we get, we remove this correction term. And what's the expectation of this blue quantity? 0. Right? And if W twiddle S is, and every once in a while we're going to update it. So think of W twiddle S as a best guess at the optimal point. We can take out this blue term, because it just means 0. We can always modify the algorithm this way. But it has the magical property that if we're at the right point, this is 0, and we don't move. Right? So it's really just intuitively, we're just trying to take our guess of this bias, but we can take it out in a mean 0 way. That's the cute trick. Right? Because this blue term is always mean 0. So, the blue term is mean 0. The algorithm is always making progress because you are following a stochastic gradient descent. And when you're near the right answer, you basically are moving a lot less. Okay, so is the intuition clear? Yep.
How big is M?
So that's the cool thing. It's basically constant. It's sort of which is nice. Basically, a lot of the computation is spent here, and then you just take some constant number of steps. Okay? So the main point is this algorithm gives you essentially linear convergence. Sort of each update, you're cutting your error down by a constant fraction. Yep. Okay.
How would this compare to just using that gradient in the first step and descending down that gradient to compute W total S plus 1?
Sorry, using which?
So using the gradient computed at the first step.
Yes.
And descending down that gradient.
So you mean like a batch gradient?
Right, so you're computing that.
So this is costly.
This is costly.
Because you have to pass through the data set. But you don't do it very often.
But you do that. So I'm asking how would the W bar S plus 1, which descends down that gradient from W twiddle S, compare to this W twiddle S plus 1?
Follow the...
So another algorithm would be to compute this gradient in the first step.
Yes.
And descend down that gradient.
That's basically batch gradient descent. Yes, and the point is batch gradient descent is very costly computationally because every update involves passing through the data set. So the point here, I'm not going to go into the details, but this essentially summarizes the style of guarantees which many algorithms have achieved over the last few years, which are ways to kind of amortize passing through your data set to make progress. Okay. But again, I just want to get to the statistical thing. What about the statistical rate? Because we have to keep the data set in memory. We still have to pass through it many times. And all we care about isn't the sum of convex functions, some expectation. Okay? But this algorithm basically gets the same sort of guarantees as these dual coordinate ascent methods, but it's a primal only algorithm. The reason I mentioned it is it's primal only because it's primal only is it adapts very easy to the statistics question. Okay. So now we're back to the statistics question. We care about the expected loss. We can only get one sample at a time. But look, it's kind of intuitively clear. There's a reason I presented SVRG rather than coordinate ascent. It should be intuitively clear. The thing to try is that you just get an unbiased sample of the gradient. And this is the modification. It's all you do. You have your best guess at the optimal point. You use some number of samples to get an estimate of the gradient at L, and use that to correct. And note at the beginning, you shouldn't care about estimating this too accurately because you're far away from the right answer. Right? But if you're near the right answer, you don't want to move. And that means you had better draw lots of samples here. So it's really two phases. What do? Where you draw a big sample, a fresh sample of points, compute the gradient at that point, and use that to correct your updates, and just run a few more points. Again, a constant number of updates, and just update and repeat. And every time you go here, just increase your sample size by like some constant.
Question. So even in the computational stage,
Yeah.
without the statistics,
Yeah.
you could have done this, right? Step one.
No, because step one, you're passing through the data set.
No, but instead of computing the loss for the entire data set, you would take a few samples and compute the gradient of the loss.
That's right. And if you did that, you wouldn't get linear convergence
Or you wouldn't? Okay.
because you're bouncing around.
Okay.
But we can't expect linear convergence here because it's a statistics problem. And that's why the analysis is actually quite different, because even if you start at the optimal point, you move doing this.
Oh, I see.
But this should be clear. It's clearly single pass, because there's nothing in memory because you're just keeping track of an average. It's trivially parallelizable because pretty much all the effort of this algorithm is computing this average. And I won't go through the... Yeah, Elaine?
Yeah, so you mumbled something about like increasing the subsample size.
This, yes.
Is there some intuition there?
Yeah, because if you start at the right answer, you don't want to move. But you have to move because the data's noisy. So the reason you're drawing more samples is...
You have to do more, but at what rate?
Oh, so you can just use double it by a factor of 2. So basically, that trade-off determines how fast you kill the initial error. So you can use a factor of 3, and the lower order term is going to look like n to the p. I just want to wrap up right now. So I just want to point out that basically just double the sample size. The rate at which this algorithm convergence is like, some constant times sigma squared over n. It depends on the initial error it's killing the initial error by n to some power p, which is determined by how fast you're doubling these things. Somehow the right thing to do is only increase the sample size if your gradient looks like it's near 0. Like do a hypothesis test on it. And then you could even almost get this exponential. But basically the point is it's a super simple algorithm. In one pass, it really does give you sigma squared over n times a constant. It'll kill the initial error. It is easily parallelizable because, look, all the effort of this algorithm is coming in this step. It's easy to parallelize, and this is a constant number of steps.
The number of updates that you really would do is like logarithmic, because you're sort of... Think of the number of updates as a function of the sample size.
Look, this is a fair statement. Like it isn't logarithmic. We're actually counting things by the samples. Just think of a streaming algorithm. Every time we touch a point, that's what you count.
Sort of half of your work is on your last bench size, right?
But that's what it should be.
So the number of times you're updating is just logarithmic?
No. You're updating. That's the number of updates of phase 1. You're updating gradients here. So let me just come back to that in the question section.
How sensitive is that to the choice of Ks and N?
No, these are super robust because here you're just doubling. See, the main point here, yeah, the bond changes, but the main point is this algorithm is nice because it's a constant learning rate. This is really what's important in practice. It's working for a constant learning rate. The algorithm is making progress because it knows it's making progress, not because you're kind of turning the learning rate down. So I think, yeah, in terms of actually putting in packages, you have to set these parameters, but I think there are ways around it by just doing a hypothesis test. Okay, so let me just take that to the question section. So the bottom line is this at least shows that you should be able to get the rate of the ERM in one pass, and I think it is progress toward automating our most basic ML algorithms, putting them in packages. This is joint work with a number of very talented colleagues. Roy Frostig is a graduate student at Stanford. Ranga is a postdoc with us at Microsoft New England. And Aaron Sidford is a graduate student at MIT. All right, thanks.
So one of the reasons why vanilla is parallelizable is because the individual little gradients are very sparse. But here, when you introduce the extra term, you're sort of killing a little bit the sparsity.
It's still parallelizable. You just have points on different. You don't need sparsity to parallelize this thing.
Well, that's not entirely true, right? In the Hogwild paper, sparsity was one of the main reasons why you could really see linear speedups.
Yeah, but that's the thing. You don't need. In some cases, sparsity can help, but here you can parallelize without sparsity because this is sort of Yeshai's point too. Is because most of your time is spent averaging and not doing the updates. That's why parallelization is possible.
Can you comment a little bit about what's the difference between doing something like this versus just running like a batch stochastic gradient descent and increasing your batch size over time?
Yeah, so this is a good question because somehow we don't have any better guarantees for increasing the batch size. In a sense, it's trying to get a little more second order information in this algorithm because it's like a 2-point difference algorithm. But mini batch really doesn't buy you much in these settings. And even in the numerical sense, mini batch, even in practice, we know this. The best batch size is basically 1 in practice. The only reason we do batch size is if we have GPUs. It's sort of a...
Okay, so let's take any other questions offline.